correct 啊。Okay.
小心啊，会打掉来啊。
没，还有因为我sorry。
Okay, so then this is the title of the talk. Okay, so this is the outline. So in this talk, you will do a brief introduction of the topic that you have investigated. Then in the next section, we will deal with the definition of the Lebesgue outer measure and then some of the elementary properties. Okay, third one is that we will speak about the sigma algebra of the Lebesgue measurable sets.
So we'll explain what sigma algebra is, right?
Later we will see how. Then the fourth one is that we will touch on Borel algebra, and that will be the end because this will give a very brief first introduction of the Lebesgue measure. In the actual report, we have actually done more work beyond the Borel algebra, namely we have actually proven more properties about the Lebesgue outer measure and measurable sets, including the inner and outer approximation theorem, and also we prove the what did we prove?
Non-measurable.
I think we proved the existence of non-measurable
Measurable
sets in addition. So of course this talk only can cover the first few sections of the chapter 3 of the report. Then you will draw some conclusion. Okay, regarding the topic, we begin by looking at the length of intervals. So the length L of interval I is defined to be the difference between the endpoints of this interval if I is bounded. Otherwise, if it's not bounded, we define it to be infinity. Okay, so here's a picture of one typical example of an interval. In this picture, we show a closed bounded interval AB. So in this case, the length is just B minus away A. But of course, there are also other variations of this interval. For instance, I can be a half open, half closed, and both open. And in this particular case, A and B can actually take on the values of infinity. So when it is unbounded, then we just define it to be an infinite length. So this is the definition that we know of the length interval. Okay, the whole business of this investigation of the Lebesgue measure is to generalize this concept of length of interval to cover length of sets. So length must first be viewed as a function. What kind of function is it? It's actually a set function. So by this I mean that it's a function that associates an extended real number to each set in the collection of sets. So ideally in this case we will take an interval and then we will send it to its length. So in this case the domain, it will be the collection of script I of all the intervals. So this is the first move that we did, and we want to extend it. So how do we extend? We extend the function length to a larger collection of sets of real numbers, not just only the intervals. For instance, the length of an open set can be defined as the sum of the lengths of the countable open intervals that it composes. Now in topology, on the real line, we know that every open set can be written as a countable union of disjoint open intervals. Example, in this case, a family of intervals ik, where k run from 1 to infinity. So the measure or the generalized length that we have in mind of this union of these intervals, which is the open set, should be computed by taking the infinite sum of all the lengths of this interval that composes it. So in this project, I learned how to construct first a collection of sets called the Lebesgue measurable sets, and a set function of this collection, which is termed as the Lebesgue measure, and we denote it by M. We wish that this function M will possess three very natural properties. The first thing, the measure of the interval is actually its length. This means that the measure as a function will be restricted to sets of the form AB or any interval is just equal to its length that we defined at the very beginning. Moreover, we hope that each non-empty interval I is Lebesgue measurable, and the so-called measure is just coincide with its length. The second wish list property that we have for M is that the measure should be translation invariant. This is geometrically intuitive. Imagine that you have a set E which is Lebesgue measurable, and you consider any number y, and you define the translate of E by y to be the shift of the set E by y units. So this means that every number in E is added on y units to form the new set E plus y. So intuitively, this set should have the same abstract length as the original set E. In other words, this E plus y, which is the translate of E by y, should also be Lebesgue measurable, and the measure of this translate should be equal to the measure of the original set. So in this sense, the measure is invariant under translation. That's why it's called measure is translational invariant. The third property that we hope to have is that the measure should be countably additive over the countable disjoint union of sets. So if we are given a collection, a countable collection of disjoint intervals of this disjoint Lebesgue measurable sets, then we expect that the union of this family should have a measure that is computed by taking the sum of the individual measure of the composing sets. This is likened to the situation that when you take the measure of the countable intervals, it's just equal to the sum of the lengths of this interval. So you should naturally extend to this particular equation. We hope that this is also true. Now, let us first speak about a special kind of open cover before we introduce the definition of the Lebesgue outer measure. So for a set A of real numbers, consider the countable collection, which is a family ik, where k range from 1 to infinity, of non-empty open bounded interval that cover A. So in this case, we can imagine that A is actually a subset. More formally, that is a subset of the union of this ik, as k run from 1 to infinity. So for such a collection, what we consider is that the length, sum or lengths of this interval to be the quantity that we want to calculate. So since the length are all positive numbers, so each of the sum is uniquely defined, which is independent of the order of the terms. So in this particular case, formally we define the outer measure of a set A. So the outer measure of a set A, which is denoted by M star A, is to be defined as the infimum of all the sums that is, you say that M star A is inf of this sum computed for the lengths of the intervals, where these intervals union can cover A. So that is the definition of the outer measure. We can imagine that because this infimum is taken over families of intervals that's covering A, there are many such families. The intuition is that we will select the infimum, which is the greatest lower bound of these computed sums. So it should be actually as small and as close to the ideal length of this set as possible. Now, before we continue, we draw from our experience some inspiration from probability theory. The Lebesgue outer measure reminds me of the probability function, in the sense that the probability function is also a set function which assigns a non-negative real number, which is no more than 1. This number is denoted by P of A, to each given subset A of an event space epsilon. So you can imagine that P is a function from the domain of all the event space, and send it to the real number which is positioned from between 0 and 1. So we call this measure of likelihood of occurrence of A, event A, the probability of A. Yes. So it is well known in probability theory that, number one, the probability of the empty set is actually 0. If an event A is contained in the event B, then you expect that the probability of the event A is less than or equal to the probability of the event B. And the last property is that if you have a countable family of events, then you expect that the probability of the union of this countable family should be no more than the sum of the probability of each individual events. So this is what we actually learned from probability theory, and it's very well known. Now, the aforementioned analogy is appropriate because it turns out that the Lebesgue outer measure M star will also satisfy the following elementary property. First, M star of the empty set is 0. If A is a subset of B, then the M star A is less than or equal to M star B. We call property number 2 the monotonicity property. Number 3, the M star of the union of a countable family of sets EK is no more than the sum of the individual M star of the EKs. So this one is actually known as the countable subadditivity of the M star. Okay, now let's pause to check whether M star actually satisfy the wish list that we already have. Okay, so let's check. So the wish list, so this property in the actual presentation, you should take time to explain this 1, 2, and 3, how you arrive to it. If supposedly you want to show the proof, you may want to select to show either one of these, but not all, so you don't waste time. Okay. Now let's pause to check whether M star satisfy the wish list which we have listed earlier, and the wish list refer to the following wish list. Let's recall. The 3 wish lists are: number 1, measure of an interval should be its length; number 2, measure should be translation invariant; number 3, measure it should be countably additive over a countable disjoint union of sets. So let us now start by the first one. It turns out that there is coincidence with the length when restricted to intervals. That is to say that the outer measure of an interval is indeed its length. This is very good news. The second property is it turns out that the outer measure is indeed translation invariant, so that for any set A and the number y, the M star of A plus y, which is formed by taking M star of the A translated y units, is exactly equals to M star of A. The third property, however, is actually that subadditivity holds. So notice that in this case, subadditivity means that instead of the equality in general, we should actually have a less than or equals. This means that if we have a countable collection of sets EK ranging from 1 to infinity, whether or not they are disjoint, the M star of the union of this family should be no more than the infinite sum of this individual M star applied to each of its EK. Now note that therefore we do not have countable activity in general. Countable activity would mean that this less than or equal sign should actually by right be equality. Therefore it's worthwhile to examine very closely why the less than or equal sign actually holds. And this is one of the detailed proof, only detailed proof that we will go through for this particular talk. So let's begin with the proof. Now if any one of the EK has infinite outer measure, the inequality holds trivially. Let us examine why. If one of these terms is actually infinity, you expect that the right hand side is already infinity. And because M star of this set is always going to be less than or equal to infinity anyways, it becomes true trivially. So there's nothing much to check. Therefore, we may suppose that each of these EK has finite outer measure. So the trick is actually to look at an arbitrary epsilon greater than 0. Why do we want to do that? The reason is what we can do is that we can make use of the definition of the M star of EK. So what this means is that for each natural number K, there should be a collection of IKI covering, which is consisting of open bounded intervals, and the job of this family IKI is actually used to cover each of the EK. Notice that because M star EK is defined as the infimum of all the summation of the lengths of the IKI, therefore if you add a little bit of the epsilon over 2 to the k, you'll no longer be an infimum, and thus there should exist a countable collection such that the infinite sum of these lengths, covering lengths, should be less than this amount, which is now no longer an infimum. Now I of Ki is a countable collection of open bounded interval that cover each of these Ek. It means the collection is countable, and this is a countable collection of countable sets. What then follows is that we just need to take the M star of the union of Ek, and it's guaranteed to be less than or equal to highest definition, the summation of all the covering intervals, and this sum is computed as an iterated sum over k and then over I. And onto the next bracket, second bracket, according to our previous inequality, the summation of the Liki is actually less than m star ek plus epsilon over 2k. Then next we split the two sums and apply the geometric series to sum up the sigma over 2k over from k from 1 to infinity, which will definitely give us epsilon.
Okay.
After we done that, this shows that the m star of the union of ek is going to be less than or equals to epsilon added to the infinite sum of the m star applied to each of the ek. But because epsilon is arbitrary, therefore it follows that the left hand side m star of the union ek, it will be less than or equal to only this amount.
Okay.
We can just omit the epsilon since it's arbitrary. So this shows that the final inequality, that the m star of the union of this ek is indeed less than or equals to this.